not know how to fix that. It keeps changing, bro. Like every time. So, I'll try that. Let me see. Okay, that seems like it's working. Let's see. All right, welcome, scholars. We are officially in the home stretch, right? I think we're at the top of week. Did I put 13? Oh no, I think I put the wrong week. Let me see. Seamless. Okay, we're good. Yeah. So again, we're at the top of week 13. We're in the home stretch, right? So we only have 2 sections of new material remaining. That's this section and then one more after this, right? So we have this week of new content. We have next week, and then from after next week, we'll either be reviewing or a holiday break, right? And just kind of wrapping everything up. So this is a good time to go ahead and get caught up with everything that's on My Math Lab. You definitely do not want to be waiting until the last minute. The hard deadline for all assignments is that Friday at the end of the week of finals. Finals is the first full week of December. Generally speaking, that's how it goes. So yeah, you wanna try to have your My Math Lab in order as soon as possible. Especially, once we get into the holidays. I mean, if you procrastinate, then either you have to do it over the holidays and you won't be able to enjoy your holidays, or it might not get done, right? So this is a great time to just get caught up. Now, with that being said, if you are going back and like redoing all assignments to improve your scores or like turning in missed assignments, my recommendation is to prioritize your exams first, right? That's where you're going to get the most bang for your buck. Overall, in the whole course, I want to say your exams count for approximately 80% of our portion of the grade, right? So it's just below 80 of your overall grade. So I would prioritize the exams first. And then the thing I would prioritize last as far as going back is that homework, because the homework is going to be a lot of work for minimal points. And that's pretty much across the board, no matter where you are. Like if you're trying to improve your score, that's pretty much what you need to do, whether you're at the bottom of the end of the totem pole or the higher end. And then also, whatever grade you're trying to get, you generally speaking, you need to score above that. Like if you're trying to get an 80, you need to be getting like 85s, 86, high on up, right? On all assignments. Whatever, because you need to score higher than what you're trying to go for. Because it's kind of hard to get that score if you're scoring lower, right? Okay, I can't really think of anything else, but you should have access to all 3 of your exams. For right now, you can anticipate your final being pretty much like we've done exams 1, 2, and 3, right? So just remote for right now. I haven't gotten any word from. You can probably breathe a sigh of relief maybe after Thanksgiving. I should hear something after Thanksgiving because that's the crunch zone. Yeah, I think we come back for like a day or 2 after Thanksgiving, and then we have the reading period. Well, I think our schedule is pretty much normal because we don't meet on that Thursday and Friday. But after Thanksgiving, then we come back, we meet a couple of more times, and then the final. If I am hosting your final, which more than likely will happen again, we don't really know until after Thanksgiving. Our last class, I think, is that Wednesday after Thanksgiving, and then that Thursday and Friday is the reading period, and then the first full week of December is the finals. So more than likely, I think I scheduled the final to become available that Sunday before the week of finals, and then the hard deadline, I think, is that Friday, that Friday at the end of the first full week of finals, right? So we could check the syllabus or whatever. It's whatever dates is in the syllabus, right? But for right now, let's just go ahead and focus, and let's get through as much of this section together as we can. As usual, if you have questions, feel free to unmute yourself to get my attention and we can talk about it. Otherwise, we're going to get into the content for today. Let me check on Zoom one more time. I'm pretty sure I got some latecomers. Okay. Cool beans. Man, I really like Blackboard over Starfish. It's so much easier to take attendance on Blackboard. Starfish can be a pain. I always have to do extra stuff. I got so much work I need to do. It's so bad. Like adulting. I don't want to be like adulting sucks. So I definitely wouldn't want to go back to like being a youth. I do like my freedom, And like as an adult though, it's like everything is on you, right? You have to make decisions, and then if it's a success, then you get the glory. If things go sideways, then you got to be responsible, right? And responsible just means your responsibility just means the ability to have a creative response, right? So a lot of it is in your ability to respond. That's kind of the reason why I run my courses the way I do. I try to be lax. I try to put the ball in your court because, like, you know, this is your introduction to adulthood. You have to make decisions for yourself that directly affect you, right? You got to learn when to ask for help, and if you can't find the help, you still got to find some other way, like to get the thing done, right? So anyway, on my end, I mean, I'm kind of caught up. It's so weird because it's like I have like 7 or 8 classes, all remote. I got caught up on my grades last week, like with you all and most of my classes, but then there's like 2 after I leave with you all, I need to sit down and do. Then I need to update my videos, attendance, like so much crap. I just like, man. And so like when the weekend hits, I just like turn everything off. I was like, I can't look this up. It's gonna drive me crazy. I just be like, I swear I feel like I blink my eyes and the weekend is over. I'm like, what the fuck? It feels like we just started. But again, that's adulting, right? So you just, everybody has a way of getting through it. Okay. So chapter 3, right? So for us, for College Algebra 1, we're only going to be doing one section from chapter 3. And then when you take College Algebra 2, it kind of picks up here, right? It does a minimal review with a few sections that's I think there's at least one section that we talked about. There's a couple of sections that we did talk about in College Algebra 1 that we do repeat in our College Algebra 2. But then it just kind of picks up from here, essentially. All right. Okay. And so here we're going to be working on section 3.1 exponential functions. And as usual, I'm just doing a live presentation. But anything that I would say here live is already available in the pre-recorded section, right? Okay, and I might even just use this for my classes later, depending on how I feel. If I'm feeling winded, I might just use this recording because it's the same content, it's the same things I want to say, and I'm usually the most fresh with you guys. So section 3.1 is on exponential functions. A few objectives: 1, define an exponential function; 2, graph exponential functions; 3, develop formulas for simple and compound interest; 4, understand the number e; 5, graph the natural exponential function; 6, model with exponential functions. Another random adult thing that I experienced this weekend, like periodically, my back goes out. That shit is painful. I mean, and I haven't even experienced like the worst of it, but you can kind of feel it coming. Like I realized I was sleeping weird. I woke up early in the morning. It was like Saturday, and I could feel it. I was like, crap. So I just like canceled any and everything. Luckily, I had like done heavy lifting already, like doing yard work and helping a friend tow a car or whatever. So I was able to just like take my Saturdays for myself. And like I've learned kind of how to like manage it. When it first hit me, I used to think that it was like the bone. I was like really nervous. It's not the bone, it's the muscle. It's like the muscle is like giving out or whatever. So I was like, okay. After my research, it was like basically just like you just gotta like kind of wait it out, massage it. And so I got like this massage ball. It's like a really hard tennis ball size massage ball. And you just put it on the ground and lay on it, and you can hit whatever spot you need in the back. And that usually gets me through it. And I just wait it out. But it's just like getting older, adulting, just like, man, it's so trivial to me. You think you're indestructible and invincible, and then your body just starts aches and pains and all this stuff. You're like, what the hell is this? And I actively like try to take care of my body, eating a certain way. I ain't gonna lie, I'll be having pizza anyway, and some other crap, chicken wings and crap like that. But okay, so exponential function. The function f of this form. It's called an exponential function with base a and exponent x, and its domain is all reals, right? So, we have this f of x equals a to the power of x. The main difference with exponentials and what we've experienced in the past, we may have seen expressions like x squared or x to the power of whatever, right? Where x is the base of the exponent. Now, the difference is those are called power functions, right? Where you have x to some power, those are called power functions. The difference here is that now our variables in the exponent. So we're going to have some real number, a base, where that base is strictly positive and not equal to 1. And now our variables in the exponent. And we're going to explore, how those graphs and function, these type of functions. Okay, let's see what else we have. So evaluating exponential functions, given these functions, we're asked to evaluate these guys. For instance, for part A, if we let x be 4, 4 minus 2 is 2. So then that means we're going to have 3 squared. That result is 9. Ooh, let's grab this guy. I need, I guess this will work for now. My mind is already in like holiday mode. Like, so, you know, this happens to me like every semester as we approach the Christmas holiday and the summer break. I just shut down. I'm just like, I don't care. Oh yeah, we said it's 3 squared, so that result we got there was 9. And again, we'll do the best we can with this section. The reason I don't mind like kind of going off on tangents is because of the pre-recording, right? So whatever we don't do together, just use the recording. Hopefully you've already reviewed the recording by now. You've already done the section. We're just going through formalities at this point, hopefully, idealistically. Let G be this, find G of -2. So when X is -2, a negative exponent, what does a negative exponent mean? Negative exponent causes it to flip. It becomes a fraction, right? So 10 to the -2 becomes 1 over 10 squared, right? So that's 1 over 100, which is essentially what? -2 over 100. Is that right? Mm-hmm. So this is going to be a -2 over 100, which is like, you can say -0.02. Let me copy and paste. Hopefully this makes sense. Again, if anything is not clear, feel free to unmute yourself to get my attention. What's the simplest way to do this one? Okay. So we have this 1 over 9 to the power of a -3/2. First, let's address the negative, right? A negative exponent causes the fraction to flip. So then that's going to be the same as 9 to the power of 3/2. Okay. So then a fraction in your exponent is really a radical, right? So if we have 9 to the power of a half, that's the same as a square root, right? 9 to the power of a quarter would be a fourth root, so on and so on and so on, right? So then there's a couple of ways we can go about it. I'm going to do the square root first. So this is going to be the same as the square root of 9 to the power of 3, so which is going to be 27. Yeah, that's fine. Okay. And then the last one, I'm just going to use a calculator for that. I don't even know what letter it is. Use a calculator. Right. So you would say 4 to the power of 3.2 and you get your result. Okay. 9, -0.02, and 27. 9, -0.02, 27, and then calculator. Okay, I feel like that's fairly straightforward. So here we're asked to graph this exponential function. Usually I have this part of the suppressed, but I'm just going to go with it. So we have this f of x equals 3 to the power of x. So we choose several values of x, right? So essentially we chose the -3, -2. We chose these results. When you plug them in, we find the corresponding y. Now I feel like this would be easier to work backwards. 3 to the power of 3 would be 27. 3 squared is 9. And then you can generate all of these results, right? So then once we have our x's, several x values with the corresponding y's, we plot the ordered pair. And we get the general shape of an exponential, which is what you see here on the right-hand side. So this is the general shape of an exponential. If we think about, so notice that it gets infinitesimally close to the x-axis as we go up to -infinity. And sometimes when you look at the graph, it looks like it's touching the x-axis, but it's not. If you were to actually zoom in, there's always space between our graph and the x-axis, provided we don't move the graph up or down or anything. But in a general shape, the x-axis serves as a horizontal asymptote. As x goes off to -infinity, our graph approaches the x-axis. As x goes off to the right or positive infinity, y goes to positive infinity, right? So horizontal asymptote, as it goes to the left, it gets infinitesimally close to the x-axis. As we go up to the right, y goes to infinity, okay? The domain. So the domain of an exponential, if we consider it from the very left to the very right, how far left does the graph go? It goes down all the way to -infinity. How far right does the graph go? It goes to positive infinity. So generally speaking, the domain of an exponential function is all reals. For any x that we can think of on the real number line, we can find the corresponding y. So then if the domain is the very left to the very right, then the range of our graph is going to be the very bottom to the very top. How far down does this graph go? If the x-axis serves as a horizontal asymptote, then it gets infinitesimally close to the x-axis. Then the range, the lowest that our y value can take on, it gets infinitesimally close to zero. It doesn't actually reach zero, but it gets really, 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 really close to zero, right? So the very bottom, we would say it goes from 0 to infinity, but the 0, you got to be sure to use a parentheses. That means we get infinitesimally, we get really, 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 really close to 0, but we do not include 0, right? Okay, so the range of the exponential is 0 to infinity, where the 0 has a parentheses and infinity always has a parenthesis. Okay, let's see if we can see some more properties of exponentials. Okay, so the one we saw in the previous, we call that exponential growth, right? We had a base a larger than 1, all right? So the base of the exponential was larger than 1, and then what you experienced in the previous was called exponential growth. Here, notice that the base of our exponential is between 0 and 1, right? So the base is between 0 and 1. And then if we choose the same x values, right? We just chose these x values, and then we find the corresponding y. Now, I feel like in this case, it's kind of easier to start here. Remember, a negative exponent causes the fraction to flip, so that's really going to be 2 to the power of 3. That's where this guy came from. 2 squared, 2 to the power of 1, 2 to the power of 0. 1/2 to the power of 1 is a half, so on and so on, right? So then if we plot these ordered pairs, let's see how our image changes. So this is what we call exponential decay, right? As we move left to right, y approaches the x-axis. So y tends to 0. Again, it doesn't reach 0, but it tends to 0. Already, I'm ready to stop talking. I probably am going to be using this recording later on. And I probably shouldn't have said that now because it's going to be in my recording, but it's okay. This is all the stuff I want to say. Let me check on you guys. Put these gentlemen. Okay. We mark this other gentleman as absent. And let me let these guys in. All right. Let's keep the party going. All right. So again, this was an exponential decay. All right. So properties of exponential functions. Let f of x be an exponential function where the base is strictly positive and not equal to 1. So this is what we just said just a moment ago. The domain of an exponential function is going to be all reals. The range of an exponential function is 0 to infinity. The entire graph lies above the x-axis. All right. So notice the 0 has a parentheses on it. Since f of x plus 1 over f of x, which is going to be a to the power of x plus 1 over a to the x, but then the numerator we can break apart into a to the x times a, and then if you cancel, you're just left with a. So then what that means is that as x increases by 1, the y value changes by a factor of a, right? Again, the y value changes by a factor of a for each unit increase in x. That's fine. So for a, when a is strictly larger than 1, we call it the growth factor is a, because the y value is increased by a factor of a for each unit increase of x. So that's like the first graph that we saw for exponential function. So as we trace it left to right, the graph is going to be increasing. So we say that function is an increasing function. So the graph is going to rise as you trace it from the left to the right. As x goes off to positive infinity, y goes to positive infinity. As x goes off to negative infinity, y tends to 0, right? So I know we talked about that just a moment ago. Okay. When our base a is between 0 and 1, the decay factor is a, because the y value decreases by a factor of a for each unit increase in x. So that was like the second graph that we saw. F is a decreasing function, so the graph falls as we move from the left to the right. As x goes off to negative infinity, y goes to positive infinity. As x goes to positive infinity, y tends to 0. Each exponential function is 1 to 1. So algebraically, to show that a function is 1 to 1, if we equate two different y values and we can show that the corresponding x values are equal, then we say that the function is 1-to-1. That's called the uniqueness proof. But if we equate two different y values and we get two x's that are not equal, then we say that the function is not 1-to-1. Right? But again, 1-to-1 has an inverse, passes the horizontal line test. I feel like there's one more. 1-to-1 has an inverse, passes the horizontal line test, and every y corresponds to exactly 1x. Those terms can be used interchangeably. Okay. All right, let's keep going. Man, these properties do not stop. The graph of an exponential function has no x-intercepts, so it never crosses the x-axis, and no value of x will cause the exponential function to equal 0. The graph of the exponential function is a smooth and continuous curve, and it passes through the critical points when x is -1, 0, and 1, right? So when you look at these 3 points, it gives you a general sense of like the behavior of an exponential function. Like when x is -1, when x is 0, and when x is 1. And then you can get the general shape if it's like increasing or decreasing and so on and so on. From 4-3 and 5-3, we conclude that the x-axis is a horizontal asymptote for every exponential function of the general form. The graph of y equals 8 to the negative x is the reflection about the y-axis. So if we think in terms of transformations, if we multiply the inside of our function by a negative, that's going to cause it to flip horizontally over the y-axis. And that's where we get our exponential decay, right? Okay, so one application of exponentials is like interest, right? So the interest rate is the percent change for the use of the principal for a given period. The interest rate denoted by R is expressed as a decimal. Unless stated otherwise, the period is assumed to be 1 year. That is, R is annual rate. The amount of interest computed only on the principal is called simple interest. So simple interest is our lowest form of interest that we have. Different interest rates or calculations generate different varying amounts of money. So simple interest is going to be I equals PRT. The interest is going to be the principal times the rate times the time, right? The principal is like your deposit amount, whatever amount you're depositing into the account. The interest rate, whenever we're using a rate, is usually given to us as a percent. Whenever we do our calculations, it has to be in decimal format. And then the unit for time is generally speaking years, right? So the dollar amount times the decimal times the years. Okay. So Anita has deposited $8,000 into a bank for 5 years at a simple interest rate of 6%. So before we go into this, usually I like to share a story of the infinite scholarship. All right. So using this formula, right? So when I was a student at Morehouse, I attended this like honors program or ceremony. It was for some honor society, and part of the presentation they were doing a fundraiser, and they called it the Infinite Scholarship. And I'm thinking to myself, well, how do you have an infinite scholarship? Does it mean to go on forever? What are they talking about, right? So their goal was to raise. Let me see. So the infinite, actually, this is abbreviated. The Infinite Scholarship. All right. Their goal was to generate $1 million, right? And at that time, they had access to an interest-bearing account that earned 5%. 5% interest as a 5% as a decimal is going to be 0.05. Right? And so if they had an account where they had $1 million deposited and it earns 5% every, and say 5% every year, and say we consider it for 1 year, how much money is generated each year? Right? So what if we say $1 million? If we just move the decimal to the right, 6 places, we'll get our result. So if we have a 5, let me see, 1, 2, 3, 4, 5, 6, right? So what that means is that with $1 million invested into an interest-bearing account that earns 5% every year, that means that the amount of interest earned each year is $50,000, right? If you broke that up, let's just divide it by 12. Hey Siri, what's 50,000 divided by 12? Hey Siri, what's 50,000 divided by 12? So like 4166, right? So a little over $4,000 a month, right? Which is, that's pretty good. That's decent. Like, so if you ever find yourself owning $1 million and you get an interest bearing account that earns at least 5%, then you can anticipate, as long as you only touch you only touch the interest, never touch the principal. That means that you can anticipate whatever the pay period is, at least $4,000 every month, as long as that account is open for them to give you. So that at $4,000, you can live off of that at this day and age, right? Maybe not lavishly or extravagantly, but you wouldn't have to work. That's enough to get a place to stay, get some food, and maybe some transportation, even if you just Ubered everywhere, or if you got a car, whatever you decide to do, right? So $1 million at 5% interest is approximately a little over $4,000 every month, right? So, and again, as long as you don't touch the $1 million, as long as that account is sitting, you can anticipate to earn $4,000 every month, right? And so that was the Infinite Scholarship. That was their goal: raise $1 million, put it in an account like this, and then now they can either, they can dish out the money however they want, right? As long as they limit themselves to about $4,000 every month, then they can either give 12 students $4,000, or they can divvy it up however they want to do it, right? But Infinite Scholarship, and that's basically interest, compound interest. Some people actually make a living doing this. I know, like at least one of my colleagues, he had money like this. He donated it. It would have been better to set it up in something like this, but that's why I share it. So at least that way, you never know when and who and how this will come to pass, right? But if you ever find yourself with $1 million and you have an interest bearing account of 5%, as long as you only touch the interest, you never touch the principal, then you'll have money coming in forever. As long as that account is open, you have money coming in forever, right? And there are ways to do it. You could win a game show. I know my colleague, he was an athlete, so that's how he did it. You can go into real estate, lawyer, engineer, doctor, politician. There's so many different ways, but if you win a lottery, it's just a matter of just being aware of this setup. Once you're aware of it and you make it come to pass, there are a lot of people that get $1 million, they get it and then they lose it, right? But that's neither here nor there. It's just an interesting concept, right? Okay. So that was the Infinite Scholarship. So Juanita has deposited $8,000 in a bank account. There's actually another way. There are some techniques that people do it. I'd have to dig and try to see if I can find some of those suggestions. But if you go on YouTube, you can find people that use compound interest, and like if you commit to, it's almost like paying a car note, but it's like is developing a nest egg for yourself, right? So that by the time you hit a certain age, and you can even do one like if you're older, you can do one that matures in maybe 20 years or 30 years. Those are a lot harder, and they're not going to be as big a payout. But there are techniques where within like 20 years or so, you can have a decent sized nest egg. But it's like making a car. It's like making a car payment or whatever. I need to look into those, and I think I'm actually going to start doing that. It's time. It's like I'm totally overdue. Anywho, so Juanita has deposited $8,000 in a bank account for 5 years at a simple interest rate of 6%. How much interest will she receive, and how much money will be in her account at the end of the 5 years? Okay, so if it's simple interest, so yeah, hopefully if you have a formula sheet, it's definitely a good idea to go ahead and add that simple interest formula to your formula sheet, just for reference. And then again, one of my mentors will say every time you use the formula, write it down. So if we're doing simple interest, I equals PRT. Okay. So the first question asks us for her, how much interest is going to be on account. So her principal is $8,000. Rate is 6%. As a decimal is going to be 0.06. And the time is 5 years, right? So the unit for time is typically in years. Let me see. It's 30, 24. Add a 0. Move it back to, then right by 3, 1, 2, 3. 2,400. Hey Siri, what's 8,000 times 0.06 times 5?
8,000 times 0.06.
Hey Siri, what's 8,000 times 0.06 times 5? She's not listening.
8,000 times 0.06 times 4 is 1,100.
She missed the last one. Let's try it here. I'm trying to get it to work here. What's 8,000 times 0.06 times 5? Yeah, we got it right. 24. So when I did it a moment ago, I said 8 times 6 times 5, right? 6 times 5 was 30. So then I was like, okay, I'm doing a 30 times 8,000. So that was like 3 times 8 was 24. Then the 30 made it 240. And then the 0.06, I brought the decimal back 2 places. So I put it back to 2.4. And then times 1,000, put it to 2,400. That was what I was doing initially, but it's fine. It still worked. Right? So the interest earned after 5 years was 2,400. How much money will be in her account at the end of the 5 years? So then her future balance or future amount is going to be the principal plus the interest earned, which is going to be the 8,000 plus 2,400 over 2,400. Another thing I think about, like, how do you protect? Like, I some periodically I'll study different ways to protect like money, right? Because if you keep the cash, then it could be stolen, right? And then if it's stolen in cash, then there's no insurance. There's nobody to reimburse you if it's stolen or damaged or burned or whatever, or if it's lost or whatever. So then I think about, and again, I'm no financial analyst. You definitely need to talk to like a professional, this kind of stuff. Um, but these are just things I think about. And I saw a movie where a guy protected his fortune through artwork. So he bought like he just had like he had like a mansion castle kind of thing, and he just had all this ridiculous artwork all over the place, statues and busts and art, paintings and sculptures and this, that, and the other. And that was his way of protecting his fortune over time. Recently, I've seen people like try to encourage you to get like a stable coin, right? And like as far as cryptocurrency, whereas like where the value of the dollar will fluctuate, like 1 minute, $1 can buy you a certain amount, then 1 minute it might buy you less, right? But the stable coins are supposed to be like it'll maintain its value over time, right? But then it's cryptocurrency, so you're in that realm. Um, I've seen where people had money in the bank, but then somebody at the bank was stealing from them, like siphoning off a certain amount, like periodically, an unnoticeable amount. And next thing the person realized, most of their money was gone, and they were like, got into a legal battle. I was like, damn, how do you protect? Then you got like gold. Then it's a matter of like, how do you protect the gold? Do you put it in the bank? Like just how do you have something of value and you hold the value over time? All right. What are some people do it in forms of real estate, like owning houses, but obviously with real estate, like I had I wouldn't call her a friend, just somebody I met. They were saying, it was like three women staying in a house, and I would help them out, like fix stuff here and there, whatever. And then one day she sends me this photo, and she's like, "Yo, this my roommate tried to kill us by burning down the house, and like this house was up in flames, huge smoke." You're like, "What the fuck?" So now it's like I'm thinking, like, damn, if you had a house, especially if you had like the trick there is finding good tenants, somebody that's going to take care of the property. Because if you got people that's destructive, now that's your money is literally like your investment is going up in smokes. Hopefully you have insurance, but I don't even know if insurance is going to cover something like that, right? Because then you get into the insurance game, and their whole game is to find ways to not pay you. One of the houses where I am right now, I think the father was like saving it for his daughter, but it's been abandoned for like decades, and so now it's like falling apart. And like you know, somebody if for it to restore its value, somebody would have to essentially tear it down and rebuild a brand new house. So it's really just a plot of land essentially, or surrounded by houses like well-kept houses, like people will cut I cut most of the yards. Well, not most of, but I cut a lot of the yards in the area. I'm just like, I wish I had realized it was abandoned because I had people that could have stayed there and I would have taken care of it. Like, just let somebody house sit. People kept approaching him to buy the house, but he didn't want to sell because he was saving it for his daughter, but nobody was taking care of the property. So now it's just like, it's an abandoned house that's literally falling down. I was like, man, that's a shame. He really should have got like a quality person to house sit for him. He could have kept it in his name, still gifted it to his daughter, but you know. So now it's like, well, how could it be restored other than tearing it all the way down? Anyway, this is just some of the things I think about. Let's hang out for like about 5 more minutes, give or take. Just interesting stories that I feel like are relevant on some degree. So we explored the lowest form of entry, which is interest, which was simple interest, right? So then this next form is called compound interest. This is the interest paid on both the principal and the accrued previously earned interest. Interest that is compounded annually is paid once a year, is given by this. We're going to actually skip this formula and get to one that's a little bit more relevant. I'm going to just skip this, leave that. This one, just because we're short on time, I do want to talk about this one. So this is what we call the compound interest formula. This is like this is the same as the previous formula. It's just the previous formula that we were applying the interest once per year. But what if we applied the interest twice per year, or 4 times a year, or monthly, or weekly, or daily, or continuously, right? Continuously doesn't apply to this one, but all those others is captured by this, right? And again, that formula we saw just on a couple of slides back is the same as this. It's just it's a specified form of this one, right? So again, this is called the compound interest formula, where A is our amount after T years, P is the principal or the amount that we're depositing, R is the annual interest rate expressed as a decimal, N is the number of times the interest is compounded each year. So how many times you apply the interest in a given year, and then T is the number of years. I'm going to leave this example as an exercise, but let me mention this. So we have this example on compound interest. It says, find a future value after 1 year if the interest is compounded annually, semi-annually, quarterly, monthly, daily, right? So if the interest is applied annually, that means our N equals 1, right? If our interest is applied semi-annually, then our N equals 2. If it's quarterly, then our N equals 4. If it's monthly, then our N equals 12. If it's daily, then our N equals 365, right? And then we plug in the other components from the given problem, and that's how we would do this one, right? But the main thing here was getting a sense of what the compoundings are per year, right? So I'm gonna leave this one just because we're kind of short on time. And there was one other thing I wanted to bring to your attention. So here we introduce the exponential function e with the base e. So e is like a function in the calculator, right? So if we had the exponential function 2 to the power of x, you see it in blue. If you have the exponential function 3 to the power of x, you see it in green. So e is an exponential function where e is like 2.7. This is like long decimal. You know, it's basically between those two functions, but really close to where the base is 3, right? I'm going to leave that one. That's not what I wanted to bring up. Where is it? That's a good one. Where is it? Oh, we didn't talk about it. Okay. Okay, well, I was really trying to get, it feels like something is missing. Let me back up and see if I can find it. Yeah, there it is. How did it? Yeah, this is what I was looking for. I kind of skipped over it. This is what I was trying to get to. So in the previous examples, we saw where if we had multiple compoundings per year, how to calculate those. And then this one is if we have continuous compoundings per year. The way I remember this formula is A equals PERT. It kind of reminds me like a bar of soup or something. But then A is going to be our future amount. P is the principal. R is the rate expressed as a decimal, and T is the number of years. So whenever you see continuous compounding, that means the interest is always being applied. We use this formula. I think it comes out of, if you take the compound interest formula and you let the n's run to infinity, it tends to this number e, right? Let me see. Go back. So you would have to like rearrange it somehow. So as n goes to infinity, it looks like that second term tends to 0. I had to think about it. I've seen it. I had to think about how to, but that's essentially what's going on. But I'd have to think about the details. But you know, we don't really need to know all that right now. The main thing is that whenever you see continuous compounding interest, that we're using this guy here. Okay. So now, obviously, I kind of like brushed over a lot of the details. I would encourage you to use my pre-recorded lecture to go back to, you know, view the parts that we didn't go through exclusively together. So on, are there any questions before we kind of close out here? Going once, going twice. Let me check on you guys in Zoom one more time. I forget anybody else that I missed. Okay. So let me see. So on Wednesday, I will go through as many corresponding homeworks for this section together as we can. Next week is going to be the last of the new material. I want to say the week after that, we go into Thanksgiving. So we'll start reviewing after next week, reviewing for the final. Just, you know, I think we'll have a couple of meetings. And so we'll probably take an exam or something like that per meeting, something like that. We'll work out a schedule. But if there aren't any burning questions, we're going to go ahead and end the session here. And from one beautiful mind to another, have a great day. And I'll see you Wednesday, same time, same place. Take care, guys. Peace.